Hi, my name is Andrew Kawabata, and this is a study of robustness of graph sparsification to adversarial attacks. So what is a graph? In computer science, a graph is a formal representation of a real-world network, so the terms graph and network can be used interchangeably. Some examples of real-world graphs are social networks, where the nodes represent people and the edges represent the friendships. And some other examples would be road networks and financial transaction networks. So some applications of graphs are something like Google Maps, finding the shortest route, also friend recommendations on Facebook, and fraud detection for banks. So what is graph sparsification? Many real-world networks are very large, containing millions of nodes, billions of edges, and analyzing this much data is very time-consuming. So that's where sparsification comes in to essentially compress the data into a more computable form. So if you have a very large data set, a sparsification algorithm can carefully choose edges or nodes to remove in such a way that it maintains certain properties of the original graph, but just with less data. So what are adversarial attacks on graphs? So this is a malicious attack done by adding or removing a small amount of carefully chosen nodes or edges. So essentially, you are poisoning a graph by adding fraudulent nodes or edges to it, or removing certain nodes and edges. The purpose of doing this is, once you've poisoned the graph by adding a small amount of edges, running this graph through an algorithm will give you very different results. So a small amount of perturbations will yield significantly different results. So our research goal, since there is currently no known study of robustness of graph sparsification algorithms to adversarial attacks, we plan to do our own study. So we do this by first crafting the attack, choosing the edges to remove or add, 2, executing the attack on a real-world data set, and then 3, comparing the properties of the resulting sparse graphs to each other. So specifically, we are attacking spectral sparsification algorithm, and this is just a type of sparsification that aims to preserve the eigenvalues of the original graph. The eigenvalues of a graph are just some values associated with the graph that are important for calculations. And just something to note, epsilon is a parameter for the spectral sparsifier. If you have a higher value, the graph will become more sparse, but there will be less preservation of the eigenvalues. To create this attack, we first have to understand what an edge flip is. An edge flip is essentially the removal or addition of a single edge. So an attack consists of just choosing the edges that you want to flip. So we've leveraged existing work that helps us generate candidates for these edge flips, and then this existing work selects the most effective candidates for an attack on a node classification algorithm. However, we changed some of this code to specifically attack a spectral sparsification algorithm instead of a node classification algorithm. So this is a diagram of our attack or our experiment, where we start with the clean graph on the top right, and then perform the adversarial attack to get the poison graph, and then you run both the clean and poison graph through the sparsification algorithm, and then at the end you compare both sparse graphs to see how the properties were maintained or they weren't. So when analyzing our results, we are comparing 2 properties. So taking both sparse graphs and comparing the following properties. One is the mean squared error of the eigenvalues, essentially just measuring the difference between the eigenvalues of the graphs. So this is the main property that the spectral sparsifier tries to preserve. So a successful attack would produce very dissimilar eigenvalues. Also, the normalized mutual info score, which is just a measure of the clustering results between graphs. So a successful attack would yield dissimilar clustering results. So we did our first experiment on a Facebook social circles data set, which is just a graph, publicly available graph data gathered from a Facebook survey. So after running the experiment, we got this graph where the x-axis is the perturbation rate, or the percent of edges that were removed in the attack, versus the mean squared error. So as we expected, the larger the attack, the larger the error between the 2 sparsifiers, and also as epsilon raised, the mean squared error also raised. So this is an indication of a successful attack. Next, we analyze the normalized mutual info score. Again, the perturbation rate, which is the percent of edges that were removed, versus the normalized mutual info score. So as the rate of attack increased, the NMI score quickly became low, which means that the clustering results quickly became very different from each other, which is an indication of a successful attack. And for our next steps, as we proceed, we want to run the experiment on other data sets, and we would also like to explore the real-world implications of our simulated attacks, as well as, and most importantly, create a defense against these attacks in the real world. Thank you.